righty. Hey folks, how we all doing today? Um, it is a bright early morning here. Sun's not quite out yet, but want to make sure we got you guys taken care of and ready to go. So yesterday we looked at law of sines, and um, mathematicians started thinking, well, maybe there's other ways to tie triangles together and not just using the idea of sines. Maybe tangents or cotangents could also help us find a way to put triangles together. And so they started looking at other things and exploring other relationships. And when they did that, they found out kind of a cool one. I'm going to show you that one today. So we're going to call this whole side right here, we're going to call that B, like that, which means the opposite of it is angle big B. We'll call this A, and so opposite of that is A. And we'll call this big C, so the opposite side would be C. And so what they did was, just like before, they decided to drop a height down. So let's drop a height down from B. Oh, maybe I went a little past there. It happens. So we'll call that H. And from there, then they looked at this side here and thought, well, what if we just kind of like clean that up a little bit? We'll call that X and we'll call that Y. So we got all these different things that are kind of broken up. So essentially, B is really nothing more than X plus Y. All right, so we're going to kind of take a look at all that today and see kind of maybe some of the things that they saw. So first off, if you notice, we got two right triangles here. So let's take a look at the first one. First one looks kind of like this, where we have X and we have A and we have C. And we also have H there as well, but for the time being, we're going to ignore the H on this one. We're just going to use A and X. And they started looking and going, well, what trig function would relate these two? We've already seen before how they use sine to relate H and A. This time they said, well, if we have X and A, we can call that cosine. So cosine of C is X over A. And if you put that over 1, we find out that X is really A times cosine of C. So in other words, if we were to come back up here, B isn't just X plus Y. We could say that B then is A times C, A cosine C, plus Y. So then they took a look at this other triangle here. Let's see if we can't look at that one ourselves. And they noticed on the other side, they had another right triangle, like that. And this one had letter C, angle A, also had Y down here, and then it still had the H on the other side. On this one, they didn't necessarily, or they wouldn't have looked at it and said, well, let's put it in terms of A. They've already introduced a trig function. They've already introduced this idea of cosine C, so they don't want to have too many trig functions going on here. And so what they did is they looked at this and they thought, well, that's pretty much nothing more than the Pythagorean theorem. So they said, let's call it H squared plus Y squared equals C squared. Now, if we're looking and trying to use just the variables, the big angles and the original side lengths, that really wasn't helping us out because we have this H, we have this Y, and that's not really in terms of everything. So, but what we could do is if we go one step further up here, we can say that b times a cosine of c, that would be equal to y. And so essentially that's what they did. They said, all right, I want to place a y. Let's make that b minus a cosine c. So now they did run into a problem because they looked at the h and thought, well, it looks like I'm able to get all the a, b's, and c's and angle a, angle b's, angle c's all together. Probably need to do that for h as well, so that way we don't have this introduced variable with us. And so on that one, they looked at it, they came back and said, all right, well, how's h going to relate to some of these a's and c's again? And this is where they came back to, and they said, okay, well, looks like we have to introduce sine. Didn't necessarily want to, but is what it is. It is what it is. So sine of a is h over c, but we can potentially use that to help us at least get rid of the h value. And so we'll have everything back in terms of a, b, and c, and angle a, angle b, and angle c. So h is c times sine of a. So that means in place of h squared, you have c times sine a. And then from there, it's just a matter of just kind of cleaning up the whole thing here. And so we just start doing a little bit of algebra. So c squared times sine of a squared. Oopsie, hang on here. My fault, my fault. Well, if you notice here, kind of looks a little weird, right? Don't we have two different angles? Was there another way we could have actually done a different angle in terms of it? In which case, actually, there really is here. Come back here. Whee! What if we use angle C and side A? What would that have done for us? Angle C and side A. Get A times sine of C. Woo. Let's try that instead. Because reason being, if you notice, we get A sine of C. Now, if you notice it and you're taking a look at it here, all of a sudden, the A's and the C's, they are the exact same value here. Let's do that instead. That's actually what I wanted to do to begin with. That's what happens when you're doing math at 5 in the morning. All righty, so sine of C. Sorry about that, guys. Woo. So that came from right here as well. And then if we multiply this one out here, we get b squared minus 2ab cosine of c. And then I have a plus a squared cosine of c squared. So now we got a big giant mess here. We got cosines of c's, we got cosine squared and sine squared of c. We've got all these a's. But if you notice, I have an a squared here and an a squared here, and they're with this sine c squared and cosine c squared. If we start to put those together a little bit, and we haven't talked too much yet about different trig relationships, but there was a trig relationship you guys learned back in integrated 2 that somehow tied cosine and sine together. It's going to be one that we're going to have to use here in 1 second. So, friends, all of a sudden I look at it myself and I notice that, hey, we have this, they both have a squared with this. So what if we were to factor out the a squared from just these first two terms? If we were to do that, the a squared would come out, and what we'd have left over would be sine c squared plus cosine c squared plus b squared minus 2ab cosine c all over or equal to c squared. We got to go back to the vault a little bit, and back in integrated 2, we said that this thing looks like is a special thing called a Pythagorean triple, and we found out back in integrated 2 that sine c squared, and we are going to look at this more this year in a few weeks here, all these different identities. But this was an identity we learned back in integrated 2. We found out that this sine c squared plus cosine c squared was equal to 1. So this special little identity here, we can use it, that we learned back in integrated 2, we can use it here to help us out and find out that a squared, this whole thing right here in parentheses, is actually equal to 1. So the big ugly, all the sine c's and cosine c's, they end up going away. And we get something very similar looking to the Pythagorean theorem. It just has this extra 2ab cosine of c. So a squared plus b squared minus 2ab cosine of c equals c squared. And friends, this thing that we find here came to be known as, just like we had a law of sines, well, this one has a cosine in it, so we call this the law of cosines. And this is going to be the thing that we're going to play with today. So again, just like with law of sines, I don't want you to think these things just kind of come out of nowhere. They do come from somewhere, right? So this is called the law of cosine. And this is going to be what we're going to be using today to walk us through some of these things. So we head on back here, and you can see this right here then is our law of cosines. The nice thing about law of cosines, unlike law of sines where sometimes you get the ambiguous case, for law of cosines, that's not ever going to be true. There's only one triangle ever. You can only have one triangle. That makes life a little bit easier, because now as soon as you see you're dealing with a law of cosines problem, you look and you say, oh, well, fantastic. Law of cosines, I only got one triangle. Don't even worry about trying to find the second triangle. So when we use law of cosines, it's either when we know all three sides, or if we know two sides and the angle in between. And again, it doesn't have to be angle C. It could be any angle, as long as we know the two sides on the opposite sides of it. So if we know those information, three sides or two sides and the angle in between, that all of a sudden tells us it's a law of cosine problem. So let's take a look at this first one. We know that A is 45. We know B is 32. And we know C is 15. And you're asked to find all the other missing parts. Well, friends, all of a sudden when you look at it here, we know all three sides makes it law of cosines, and it means that there will be no second triangle. Law of cosines will never have a second triangle. Law of sines can. That's that ambiguous case that we talked about yesterday. But law of cosines never can. Other general rule, for instance, if you ever start a problem with law of sines, you stick with law of sines. However, if you ever start a problem with law of cosines, we will stick with law of cosines. So once we decide we're using law of cosines, we're going to use that the whole way through. Now, I'm looking at these three angles. It doesn't matter what angle you do first. I usually go for the angle that's going to be the biggest, and that's always the angle that's opposite the biggest side. So I would have gone for A first. So I'm going to use this one right here. I'm going to use that law of cosine problem. I want to find for angle A. So 45 degrees equals 32 squared. I said degrees squared. 45 squared equals 32 squared plus 15 squared minus 2 times 15 times 32 cosine of A. So we want to get the cosine of A by itself, friends. And in order to do that, we end up with 45 squared minus 32 squared minus 15 squared. Now you guys are going to be, when you start putting all these things together, it's very easy to want to combine all these terms. Don't do it. Remember, they're not like terms because this negative 2 times 15 times 32, it's tied with the cosine of A. So it cannot be combined with those squares. Now we need to, in order to get cosine A by itself, we have to divide all that out. So we have 45 squared. This is where that function on your calculator, the alpha y equals, that will allow you to type fractions in, really kind of comes in handy. And so we're going to do our inverse cosine to get A by itself. So that means A is the inverse cosine of all of this. And again, you can just type it literally right into your graphing calculator here to figure out what A is. We got one more day of right triangle, or not right triangles, but triangle trigonometry. And then after that, we get into what trig really is, circles. So after today, we'll have one more day of triangle trig. We just kind of tie it all up. This will be the essential skill, all this triangle trig called laws of trig. All right, when we plug it all in, we find out that A is 143 degrees. 0.933. Remember, we want all the decimals. We do not round until our final answers. So at this point in time, I know what angle A is. We go to 4 decimals again, 9.334. But now, to find angle B, I'm going to go ahead and go take a look at this side that's opposite and do the exact same thing over again. If you want to, feel free to store angle A in case you think you might need it again. You could. All right, we might need that again. Might need it for area especially, so it might not be a bad idea to go ahead and store this one. So if you want to store it, we can come back and use it later on. You don't have to. It's whatever you want to do. You might choose to use a different angle later on. Your call. All right, so we can store that as A on our calculator. So that way I know, all right, I'm going to be using that one again. And let's see here, B squared. Also going to probably need it actually for C to figure out C here in a second too. Because I only have to do law of cosines twice. I don't have to do it 3 times. Because once I know 2 angles, I can find the 3rd angle. So 32 squared equals 45 squared minus 15 squared minus 2 times 45 times 15 times cosine of B. So again, it's the same thing. Once we start law of cosines, we stick with law of cosines. And we can go through and get B by itself. the exact same way we just did with A. So B is going to be the inverse cosine of 32 squared minus 45 squared minus 15 squared all over the negative 2 times 45 times 15. All right. And that means that B then is going to be approximately 24.7493 1923. And again, you're going to probably want to store this one as well because I am going to need to use it here to help me figure out what C is here in a second. So on my calculator, I'm going to store that as B. And again, you wouldn't put these things in red on your ESA, on your FRQ, but I just want you to know what I'm typing into my calculator so that way I have it for next time. So 7493 degrees. Okay, so we found two of our angles. Well, angle C isn't going to be too bad because angle C is just 180 minus B minus A. So C is approximately, now I won't use C again, so I don't need to actually go this one out to all the decimals. I'm still going to put them out there, but don't need to. 317.26903. And the nice thing about law of cosines, again, is you only have one triangle to deal with. There never will be an ambiguous case that could be two triangles. So 3173 degrees, and then we get our area. And I'll just use that angle A. So if I'm going to use it angle A, that means I have to use the sides that are right next to it. So area is 1/2 times 15 times 32 times the sine. Now, some of you guys will actually make that cosine again. You're like, I mean, cosines, I got to use cosine. Well, the area is still sine. So sine of A. I'll be honest, sometimes when I'm just going through really, really fast, I'll make that same mistake. It happens. So I get 141.294 0198. And again, I don't need 4 decimals or all these decimals for my area, but just in case, there they are for you all. So 141, I wasn't given a measurement, so I don't have to add a unit squared or anything at the end of it. If you notice my angles, I do have the degree sign. So that is always part of an angle for a triangle. All righty. So there's our first one. If you notice down below it is example 2. So I want you guys to go ahead and pause the video. You can use this one as an example here. Pause the video and go ahead and solve example 2, and then we'll talk about it. All right, let's see how you guys did. First of all, we got to draw ourselves a triangle, figure out what this looks like. Looks like A is 115 degrees. I'll make this one A up here. 115 degrees. So B, little b is 15. Little c is 10. So I'm going to have to find angle B and angle C. And I got to find little a. Well, friends, this isn't going to be too bad. All of a sudden, I notice I have a kind of a side angle side field to it here, which means it's going to be law of cosines again. So there is no second triangle. and get rid of them right from the beginning. And we can go through and actually figure out what all these values are. So I'm going to start off, I'm going to find A here. Then I could actually find my area to begin with, because you notice they gave me all the values I need to figure out my area. So A squared equals 15 squared. Plus 10 squared minus 2 times 15 times 10 times cosine of A, which was 115 degrees. So literally, this is just plug this into your calculator and then take the square root of it. And if you do that, friends, you find that A is going to be about 21.2552 4591. So found that one first right there, 21.2552. Now, friends, I am going to need to use this one again, so I'm going to store this, and I'll store it as A. Since that's funny thing is, when you store it in your calculator, I'm going to be using a capital A. But this is not the angle A; it'll be lowercase a. So I'm storing it as A just so I have it. And then it's a matter of just figuring out which angle you like to do. Again, I usually go for the angle that's opposite the biggest side. Doesn't matter, friends. So I'm going to use 15 squared equals, I know what A is now, that's 21.2552, yada, yada, yada. But I'm just going to write it as A because I stored it in my calculator. Minus 2 times A times 10 times cosine of B. So we're going to go ahead and get B by itself here. So I'll add in that extra step there to just how it all gets separated. So 15 squared minus A squared minus 10 squared, all divided by -2 times A times 10. We do inverse cosine. And again, we just plug it right into our calculator. Use that alpha y equals button to make the fraction pop up. So that way you're not worried about trying to figure out, did you have enough parentheses or any of that kind of stuff. And you can type it in exactly the way it looks. And I'm literally, on my calculator, I'm going to be typing in A, where all those A's are. So, and when we do this, I found out that B was 39.76116. There we go. 272. So 76112. Again, we always go to 4 because even if we round wrong, the College Board on the AP Stat and Calc tests will give you credit for truncating it to 4, so you won't ever be wrong. Now, I'm going to store that again because I'm going to need that here in a sec. So I'll store this one as B here. To find angle C, it's just going to be -180 minus 115 degrees minus that angle B. So C is going to be about 25.2388. 3728. Two, 388. There we are. And again, they set up the area for us, so we didn't have to do a whole heck of a lot there. And we found out the area is 1/2 15 times 10 times sine of 115 degrees. Oh, looks like I got a kid up in the background. And we get 67.973. All right. Well, we're just about done today, friends. We're going to look at just one other little thing here. It's kind of, well, it's not really a little thing. It's honestly, it's a phenomenal theorem. And it's not one that I'm actually going to prove for you guys. You can look this one up. It takes a little bit longer to prove, but it honestly is just an algebra theorem. It's not, you guys know enough math to be able to pull it off. It's just, it does take a little bit of time. But this guy, a Greek mathematician named Heron, he found how to find the area of any triangle knowing just the sides of the triangle without using trig at all. And it can be any triangle. And he basically said, hey, what if we add up all the sides and divide it by 2, we'll call that the semi-perimeter. And using some algebra 2, honestly, literally what you learned in integrated 3 and algebra 2, you could do this. He was able to figure out the area of that triangle. And it's really pretty darn cool. So let me show you how this works. So first thing you want to do is you want to find your semi-perimeter. I always use a cursive S because my S's, well, they don't necessarily look good. They always look like 5s. So friends, here's our sides. So we're going to find that semi-perimeter. So we're going to add them all up. 8 plus 13 plus 15, and we're going to divide it by 2. So if I divide that all by 2, I find out that S is going to be 18. So the area of this triangle then would be about, I shouldn't necessarily put about, it actually is. When I get my decimal answer, it'll be about later. It's S. And then amazingly is each side minus that semi-perimeter. So 18 minus 13. I'll start off with 8 first. We'll go in order. 18 minus 8. 18 minus 13. And 18 minus 15. Heron's formula is really, really cool because now using Heron's, as well as using the sine one, I can find any triangle I want to. Don't have to use base times height divided by 2 ever again. All right, so we clean this up just a little bit. We get 18 times 10 times 5 times 3. And if we do that, we end up with our perimeter of about 51.9615. It's just kind of a cool little formula. another little thing I thought, yeah, that'd be kind of a fun one to know. And again, it is helpful. So this was what? 8, 13, and 15. So that was the area of that triangle. So let's go back now. Let's take a look at some here briefly. Let's go back to that very first triangle we had. The very first triangle that we were solving today with law of cosines. If you remember, it was all three sides. We were told that one side was 45. We were told that one side was 32, and one side was 15. Well, maybe not drawn to scale here. And we had to use this angle A here to help us out here. And if those of you guys don't remember what angle A was, I'm going to put it back up there for you. Angle A was 143, and I had that stored in my calculator, 0.933. So we had to do a quick little 4117. We had to do a law of cosine problem to figure out what angle A was, and then we were able to use our law of sine, or not law, we were able to use our sine formula of area to figure out what the area was. My guess is you're probably already guessed what I'm going to have you do here. Then after that, we'll call it a day. So 32, 15, and we had sine of that big ugly thing. Point 9334117. We found out that that area was 141.2940198. Well, if I gave you three sides, that kind of looks like it may have actually been a Heron's formula problem you could have done. So why don't you go ahead and pause the video and see if you can use Heron's formula for that original triangle. All right, let's see how you did. First up, you had to find the semi-perimeter. So 32 plus 15 plus 45 divided by 2. That would have ended up being 46. And then we find the area by plugging it into our area formula. So it's going to be the square root of 46, and then each side subtracted from 46. So 46 minus 45. 46 minus 32, and 46 minus 15. We have 46, we have 1, we have 14, and we have 31. And when we plug it all into our calculator, we find out that the area, hopefully, is very, very close to that. 141.294.019. Turns out it was 7. So, by the way, notice 1, 2, 3, 4, 5, 6, 7. It wasn't until the 10 millionth spot that we had a number that was a little slightly different. This is actually the more exact answer here. You got to remember, because I use this rounded decimal here, that's going to throw that answer off a little bit more. This is actually the more exact answer. So kind of crazy how that whole thing works. So anyways, friends, good luck with Law of Cosines. My guess is you're probably going to like it more than Law of Sines because there is no ambiguous case. And have fun with Heron's formula, and I will talk to you guys about it later.